PhD from HRI under the supervision of Professor Sandhya Chaube, and he worked on several aspects related to long baseline physics during his PhD and did some fundamental work related to Neutrino Decay. He did some very important work exploring whether we can probe the decay scenario of neutrinos, active neutrinos, in the context of long baseline experiment. And after his PhD, he had a short stay in PRL, I hope, and then he moved to University of this Campinas to work with few renowned neutrino physicists there. One of them is Orlando Perez, and recently he has written a paper on solar neutrinos, which is very nice work. So today Dipyaman is going to tell us whether neutrino decay or not. So Dipyaman, you can start now.
Thank you, Professor Agarwala, for inviting me to give this talk, and also for this very nice introduction. So today I will talk about this search for neutrino decay at various neutrino experiments. I'll mainly talk about two types of experiments. One is the long baseline experiment, and the other one is the solar experiment. So what? So it's not moving. What's happening? Can you see my mouse also?
Yes.
But it is not moving.
So you can get out and then come back again, maybe exit from the full screen and
okay.
Try. Now you see it is changing?
Yeah. But let me try the full screen mode. I started something else. Yeah, now it's okay. Sorry for this delay. Okay, so the outline of my talk is first I will give a very brief introduction to neutrinos as a whole, and then I will give a summary of neutrino oscillation formalisms, then a brief review of what is the current status of the neutrino oscillation physics. Then I'll come to neutrino decay, and then I'll talk about two of my works, which I did, one of which is done at PRL with Professor Surabhati Goswami and Kaustav, and also Devajyoti from Assam. And the other one, which I recently did with Orlando, Pedro, and Hainan in Brazil. And then finally, I will conclude and tell something which I want to do in the future. Okay, so first of all, what is a neutrino? So we all know about the beta decay, that when the radioactive nuclei decay, it sometimes emits an electron. And before the discovery of neutrinos, the picture was like this. So there was a atom, or rather a nucleus, which emits an electron, and its atomic number gets increases. So that was the picture. And also, this seems like this is a two-body decay. So we have one nucleus at the beginning, and then we have another daughter nuclei and another electron. So it's a two-body decay. So we should expect that this energy spectrum should be a monoenergetic. But what is observed is that the spectrum is actually continuous. So that was a puzzle, and it seems that energy conservation, which is most fundamental of rules of physics, we can say, that seems to be violated in this case. So the whole physics is in danger. So what happens is that in 1930s, Pauli wrote a letter, which I have given here. This is the screenshot of this letter, where he gave a desperate measure to save this conservation of energy. So he proposed that there can be a neutral particle, which he called neutrino, and it should have a spin-half particle, which should obey his exclusion principle. And in that case, this picture of beta decay becomes completely different. So it becomes now that there was a nucleus at the beginning, and it decays into another daughter nucleus along with the electron, and now there has this new particle, which is this proposed neutrino, the hypothetical particle at that time. So since this is a three-body problem now, or three-body decay, so now we can have a continuous spectrum. And in this way, in this letter, Pauli explained that continuous feature of this beta decay spectrum. And presently, we have discovered 3 types of neutrinos, and each of these neutrinos are associated with the 3 charged leptons. So we have electron type neutrinos, which is associated with the electron, the muon type neutrinos, which is associated with muons, and there are the tau neutrinos, which are associated with tauns. So whenever there is a charge type weak interactions, so when there is an electron, the associated particles will be the electron neutrino and so on. So now we come to sometimes later, now at the present time, which is the standard model. So we have this very nice picture here of the world without gravity. So we have these 6 quarks, these 6 leptons, which are the fermions. So it has spin half, and also these force carrying particles, which are these Z, gamma, Ws, and gluons. And also we have this Higgs boson, which was recently discovered in 2012. But in the standard model, to give a fermion mass, we need both left-handed and right-handed particles according to this equation. But the problem is that only left-handed neutrinos are seen. There is no evidence of right-handed neutrinos. So if a mass of neutrino is observed, then this is clearly a evidence of new physics. And this is one of the most important reasons why we study neutrinos with so much importance. So the question is now, are neutrinos massive? So now we have to go back a little further and look at the solar neutrino problem. So what was observed that when the neutrino flux is measured from the sun, it was observed that we get almost 1/3 of what is predicted by the standard solar model. And this was a problem. So where do these neutrinos go? So this is called the solar neutrino problem. And at that time, the neutrino oscillation was proved as a solution to this problem, which I'll come later to explain what is neutrino oscillations. And I will show that the neutrino mass is required to explain the neutrino oscillations, and therefore the solar neutrino problem indicated that neutrino might be massive. Okay, so then these 2 slides, which are very famous, and these are firmly established that neutrino oscillates. So the first one is from Takaaki Kajita's talk in 1998 neutrino conference, where he showed this slide, where he showed that there is a difference between the upgoing neutrinos through the Earth, and the downgoing neutrinos from the atmospheric neutrinos. And due to this difference, he concluded that there is a 6.2 sigma discovery of these neutrino oscillations. And also another experiment, which is the SNO experiment, the Sudbury Neutrino Observatory, they measured the neutral current for the first time, and they showed that there is a difference between the neutral current and the charge current. And therefore, this plot shows that there is a best fit, which is that there is a electron type flux, and also there is some other flux, which is basically the combination of muon and tau type neutrinos. So it showed that the neutrino flux, total neutrino flux, that is the neutral current flux, which is observed in the Earth, that is not only comprised of the electron type neutrinos, but also these muon and tau type. But in sun, there is no other types of neutrinos like muon and tau. So we showed that some of the neutrinos converted during the flights, and this firmly established that neutrino oscillates. And this discovery was of 5.3 sigma its significance. And for these 2 gentlemen, Takaaki Kajita and Arthur McDonald's, awarded Nobel Prize recently. And this also established that neutrinos are massive. Okay, so now I come to the neutrino oscillation formalism. So this was first put up by Pontecarvo in 1958. So this is very old. And for this, we need 2 assumptions mainly. The neutrinos are massive, and the neutrino mass eigenstates that should be different from the interaction eigenstates. So there should be some linear relationship between them. And so we can write that denote these mass eigenstates by this nu1, nu2, and nu3, because we have 3 neutrinos, and flavor eigenstates, which by nu e, nu mu, and nu tau. And I shortly denote them by nu I and nu alpha respectively. And I can write them as a linear combinations. So I can write this nu alpha as a u alpha I and nu I, where a alpha I is the PMNS matrix. And then I can write a Schrodinger-like equations for these neutrinos, which is like this. I have written here x because x equals to CT, and since neutrinos are ultra-relativistic and C is the 1 in our literature, so it's roughly x equals to C. And this Hamilton, this H is the Hamiltonian, which is basically this. And here you see that there is this mass is coming. And we have these two mass square differences, this delta m square 2,1 and delta m square 3,1. And this U matrix, which can be parameterized in this way, and it has three parts. One is this theta 2,3 part, which is this theta 1,3, and this theta 1,2. This is measured from the solar experiments. This is from reactors. It's 1,3, and see 2,3 is measured mainly from the atmospheric and long baselines and so on. And also we have this CP violating phase, which is very important. So if I solve these equations, I can get an expression for a probability, which is this. So for neutrinos, this is this big expression here, and for antineutrinos, the expression is here. There's a little difference. This is basically that this plus becomes minus for the antineutrinos. And also, which is most important, is that here there is an imaginary part, which is this thing, and that is the source of the CP violation for the leptonic sector. Okay, and also this is for vacuum. But what happens when in neutrinos process through matter, like through Earth or Sun? So there is this CC type of interaction or charge current interactions, which is mediated by the W bosons, and there is also neutral current interactions, which are mediated by Z bosons. The charge current interactions only occurs with the electrons because the normal matter is comprised of electrons. There is no muons or tauns in normal matter. But for neutral currents, it can happens with anything. And therefore, these we can write these charge current effective interaction like this, which can be also in terms of potential like thing that which is VCC. And for neutral current, we can write this like this. And inside the matter, this evolution equation, which I showed earlier, gets modified, and a new potential term is added. And the total effective potential becomes this. Now you see this V and C is a diagonal term, and I can remove these terms, and still the solution will be same because it will contribute to a phase. And therefore, the final equations become this. But this is a very complicated equation, and it is very difficult to solve it analytically. So some approximate solutions are available, and which I show here. Now I come to the current status. And the current status is this. So theta 1,2, theta 1,3, and delta m square 2,1 are precisely known. Theta 1,2 and delta m square 2,1s are measured from solar experiments and also from reactor experiments like Camland. And theta 1,3 is measured by Diabe mainly, which is the reactor experiments. And these are very precisely measured. Theta 2,3 is known to be around 40 to 52 degrees. And it is it is going to be measured by the future experiments. And also the absolute value of delta m square 3,1 is known, but we don't know the sign of delta m square 3,1. It can be either plus or minus depending on the hierarchy, which I show here in this cartoon, where the left is for normal hierarchy and the right is for inverted hierarchy. And for the normal hierarchy, the case is like this. So nu3 is the most massive, and we have then nu2 and nu1. But for inverted hierarchy, the nu3 is the least massive, and the most massive is nu2 and then nu1. And so presently, in summary, the unknowns are the CP violating phase, the mass hierarchy, and octant of the theta 2,3. It means that whether the theta 2,3 is less than 45 degree or greater than 45 degree. Also, there are lots of possibilities of new physics, like sterile neutrinos, that is one extra neutrino states, or non-standard interactions, like the interactions of neutrino with the matter, which can be different from what is known, and also decay of the neutrinos, which I am going to talk in this seminar. So now I come to the decay of neutrinos. So the first of all, why I consider decay? Because the first thing is the neutrinos are massive, so it can easily decay into some lighter states. Also, there is no symmetry which protects the neutrinos from decaying into lighter states if there are lighter particles. So there is no symmetries. And also, the limits on the decay lifetime is not so strong, at least for nu3. And so there are lots of parameter space which is available and we can explore as a phenomenologist. So in the first part of my talk, I'll talk about this invisible neutrino decay. So here, one active neutrino states, that is either of the nu1, nu2, or nu3, it can decay into some sterile states, which is this nu4, and another scalar particle, which I call this J. And together I can write this as nu alpha and nu s. So nu alpha is this 3 active states, the flavor states, and nu s is this new states. And I can write these together using a matrix notation like this, where U is the usual standard PMNS matrix. And the important thing to notice is that here there is no mixing between the active states and the sterile states. So in this picture, the evolution becomes
in the previous slide, go back.
Yeah.
So why you have to take anti-neutrino here? Like nu3 can go to nu4 or plus Majoron kind of thing, right? Why it is nu4
yeah.
bar?
Yeah, actually, when I talk about the solar thing, there is both the type of things. So I'll show there. Okay.
But in principle, the heaviest state, you are considering that nu3 is heaviest, right?
Yeah. Yes.
So you are working in normal mass ordering scenario.
Right.
Okay. So then that you should mention that. Okay.
Yes.
That you are assuring.
Yes.
Normal mass ordering. So let me understand. So you have M3, and then M3 is the heaviest, and it is decaying to a lighter guy. But
yes.
What is the mass of this M4? Like it is between 2, 1 or anywhere. So what is the splitting? Like if I arrange it, like I have M1, M2, M3.
Yes.
Now M3 is decaying to something should be lighter, right?
That's the only assumptions, but
right.
There is no constraint on the mass from at least my analysis.
Right. So this M4 or nu4, the mass eigenstate of the nu4,
yes,
that can be anywhere. Like it is below M1, much below, or in between M1, M2, anywhere, right? It can be anywhere.
Yes, from this perspective, it is true. But I don't know what will happen if other types of physics comes in, right? If it is between M1 and M2, there might be some other problems.
No, but you don't need to worry about that when you analyze the situation. Like M3 is decaying to another invisible guy. Basically, yes. You can call it sterile maybe, and a Majoron, yes. Right?
Right.
So what is the value of M4? It doesn't matter in your phenomenology?
No, it doesn't appear in my analysis anywhere. At least in this part of the proc. When I talk about the visible decay, it will matter. Actually, I'll see. We'll see.
Okay.
Okay. So yeah. So the evolution in presence of decay becomes this. And now we have this extra term, which is this, where this mass of the heaviest guy comes in, and also the lifetime of this guy. So, okay, so here I have mentioned that this is normal hierarchy, and also the mass matrix and the decay matrix can be simultaneously diagonalized. This is an assumption. So now I'm coming to the first work, which I have done with Shubhabhuti and Kaustubh and Devajyoti. So in this case, we can write this, we can solve this equation approximately for the 2-generation case and write this like this. So the important things to note here is this, the presence of these exponential terms, which is due to this decay, and which is dependent on L by E. So when you have lower energies and higher baselines, we have large amount of decays. And also there is this correlations between this theta 2,3 and these alphas. So this will become a problem for determining the theta 2,3, which I'll show in the next few slides. So here I show the appearance probabilities. The left figure is for the experiment which is at first oscillation maxima, and the second one, the right one, is for the one which is at second oscillation maxima. So basically this, since the baseline is higher in the right, so this left figure basically gets stretched out, and so I get this figure. And here I show for different kinds of alpha values, what is the probabilities in the two cases. And also this LO and HO are for the lower octant of theta 2,3 and higher octant of theta 2,3 respectively. And we can already see that there are some different behaviors of probability when in the same range of energies. This is for the disappearance probabilities, and the same levels are here. And also there are some differences for the first oscillation maxima and the second oscillation maximas. So now I come to the statistical analysis of our work. And so we define this chi-square stat as this thing, which is the end test is the test number events and n true is the true events. So that the true means that this is the events we generated using our simulated data, so using some parameters. And also we have these systematic parameters like this normalization error and tilt errors and etc. And this chi-square is basically the likelihood ratio, and so this chi-square should follow a chi-square distribution according to the Wills theorem. And also I've given here the different systematic uncertainties which we have taken for these three experiments. So
Dipyaman, I have a question. Actually, I was thinking about the Hamiltonian you showed. Can you just go back? Like I'm going slow a little bit, but yeah,
this one?
Yeah, this one. So you have a decaying state, right? So if I see this Hamiltonian,
yeah,
this part, so okay, so you have like some part which is Hermitian, and this decaying part is anti-Hermitian, right?
Yes.
So my point is this. So you have now, Hermitian and anti-Hermitian components are there, no, in this effective Hamiltonian.
Yes.
So how will you diagonalize this with some unitary transformation? So you do it numerically, or you have some analytical expression when you have matter also for for all matter density. Can you have like uniform transformation when you have Hermitian and anti-Hermitian component?
No. What I have done is that I have used numerical recipes, which I solved it by Runge-Kutta method, not by diagonalizations. So a brute force a solution of these equations I have used.
So you have numerically solved it, but but you showed some analytical expression, no, or somewhere. So that is like in vacuum or two flavor or something, right? Or what?
This one, yeah, this is for vacuum and also for two flavors.
Okay, I see. So
and this is approximate also.
Okay, so okay. So when I want to do it with matter, when you have matter,
yes,
and you have also, you understand, right? When you have a decaying state, so you have Hermitian and anti-Hermitian component in the effective Hamiltonian,
right?
And with the same unitary transformation for all matter density, it may not be possible. So you have to do some assumption or approximation there. And
but it can be also a non-general matrix like U.
No, that is my point. Like,
Yes, yes.
When you're at the same time that the state is also decaying, right?
Yes.
So I think you can't diagonalize simultaneously this Hermitian and anti-Hermitian component.
Yes.
If you have a decaying neutrino by a unitary transformation.
No, but we can use a general matrix, not a unitary matrix. In that case, it will be not a dagger, but it will be inverse.
I see. Okay. Yeah, I was thinking how to get the analytical expression, basically compact analytical expression in presence of matter.
I think Kaustubh and Amol and Babut was doing something, and they have recently wrote an article also written.
Okay, they
in
have
this.
done some work. Okay, so then okay, we will discuss after the talk with them. Okay, you can point out that.
Okay.
Okay, go ahead.
Okay. So this is the sensitivity plots for so T2HKK and ESS. I have in the left, I have done this for.
What is alpha?
Alpha is 1 over the lifetime. So this is basically the decay rate.
M3 by tau 3 or what? No.
Yes. I think it's a 1 over tau 3. Not M3 is not there. Or yeah, no, it's M3 by tau 3.
Oh, so just go to your Hamiltonian. Let's see the dimension.
Yeah, this is because alpha L by 2E, and so alpha contains the M.
Yeah, so alpha, if you go back into your three flavor equation, yeah. So are you probing M3 by tau 3, this ratio, right?
Right.
So this is your alpha. I'm just trying
to. So right.
This is your alpha.
Right.
So then alpha has a dimension of EV square.
Yes.
Okay. Yeah, that makes sense. So you have
yes.
Because otherwise you have to fix M3, right? So you can't do that. You don't know.
Yes. So alpha is M3 by tau 3.
Okay.
Okay, so the left one is for lower octant, where I have taken this value of sine square theta 2,3, which was at that time I think the best fit value, and this is sine square theta 2,3 for 0.56, and these are the true values. So we generated the data using these values, and in the fit we have marginalized over the theta 2,3s. And the interesting things to note is that here is this thing, which is this sudden bend of the sensitivity for ESSnuSB, which is second oscillation maxima experiment. T2HKK is a combination of first oscillation experiment and the second oscillation experiment, because it has two detectors. One is at 295 kilometers, which is first oscillation maximum, and the other one is at 1100 kilometers, which is a second oscillation maximum, and both are identical detectors. So they are basically sum of one first oscillation and a second oscillation maximum. So, but for the ESSnuSB, we see these things. So we wanted to see why this is coming. And in the next few slides, I will try to explain these features. So here I have done this. So L1 and L2 are basically the two detectors which I was talking about. Of this one is L1 is at 295 kilometers and L2 is at 1100 kilometers. And we have plotted their sensitivities for both lower octant and higher octant. And this red one is for L1. The greenish one is for L2. The blue one is for actual T2HK, okay, where we have combined both L1 and L2. And this other one, which is this dotted gray line, which is basically the sum of the chi-square of L1, basically this line and this line. And for the lower octant, there is not much important things to observe. But in the higher octant, there is this thing, which is very important. So we see that when we combine the two detectors, we see that the chi-square gets increased and we get these blue lines. And this is called a synergy. So why is this coming? So what is the explanation? So here we have further explored this, and I have plotted for a particular value of alpha, which is around this value. So this range and this range. What is the chi-squared with the sine square theta 2-3 test? And this is for lower octant, and this is both are for lower octant, but this is for L1 and this is for L2. And we see that not much is happening, and this green line is basically this line, L1. The value of this minima gives the point here and here also. And we so for the lower octane, not much is happening, but for the higher octane, things becomes interesting. For the L1, it is not much happening, just theta 2-3 is shifted a little bit. But for the higher, for L2, that is the second oscillation maximum, we see a completely different kind of behaviors, and this the minimum of the theta 2-3 comes to the opposite octant. So it's shifted to the opposite octant, and we get this is the minimum. And therefore, we get this line. So where it suddenly goes low at a lower values. And so we try to explore this further. So so this is at what's happening at the lower octant for L2, and that this the red lines are for the appearance channels, and the blue lines are for the disappearance channel. And when we sum them, we get this not sum. When we take them together, we get these green lines. And we have shown for two values of alphas, which is one is 10 to the minus 5, and which is slightly higher values, which is this value, and we get these two lines. For higher octant, now what is the case? For higher octant, we see that for in the disappearance channel, this same similar behavior is observed, which is this. So we get the minima in the opposite octant. Yeah, but for higher values, for lower values of alpha, what is happening is the appearance channel is dominating, and therefore the appearance actually pushes the theta 2-3 in the opposite octant a bit, and therefore the minima is observed at the lower at the higher octant, and therefore we get this part, which is high. But when the alpha gets higher than a certain value, then the effect of appearance is lost, is not that high, and therefore this effect of shifting the chi-square up is not happening too much, and therefore we get the minima in the opposite octant, and therefore we are getting this, where this chi-square becomes lower above a certain values of alpha. So this is the main observation from our analysis. So next, we are showing here the role of alpha in the determination of theta 2-3. Earlier, I have
that synergy, whatever you are saying between L1 and L2, like between basically your JD and KD, basically.
Yes.
So this synergy is coming, I believe, when you are performing marginalization in the fit over several parameters, and the presence of KD restricts some parameter space, and you can call them the synergy at the oscillation parameter level, right? I think this is the
no. What is happening is actually the not KD. KD is not KD is allowing this synergy to happen. But when we add JD, I will show in later that it goes away, because JD can measure the theta 2-3 very precisely.
No.
So the effect of
with only KD doesn't exist.
No, we are trying to see what is happening. So yeah, in realistic situation, it helps actually.
Yeah,
the T2HKK helps.
Yes. So my point is, the way I see that you have T2HK that is going to happen. It is funded, and
Yes.
this is one detector at 295 kilometer. Now
Right.
you are eating a slice of the cake at Korea. They are
Yes.
not going to change the beam for Korean detector. The same beam will go, and whatever
Yeah.
slice you can grab, that is up to you. So, but
Yes.
you put another detector there. So
Yes.
KD doesn't exist without JD. So,
Right.
so to me, JD is fine, or JD plus KD is fine, but
Yes.
only KD doesn't exist basically, right? Because
Exactly.
so this is where I'm thinking that you have a merit of JD plus KD over JD, because
Yes.
some parameter space get restricted when you combine.
Right.
But that is fine, that I understand. So, but when you say synergy, from the experimental point of view, these two experiments have some synergy because they are seeing the same flux
Exactly.
at both the experiment.
Right.
So, some systematic errors are common in these two experiments. Okay.
Right.
So I'm asking that, do you consider the correlation between these two experiments, or you treat them as a independent experiment when you do the analysis?
No, for systematics, we didn't consider any correlations. That's
So these are basically
the case.
two different setups for you.
Yes. But here the case is coming due to the Theta-2,3. So that is taken into account.
That means this is in the fit. In the fit, when you have both the experiment, then somebody is trying to restrict some parameter space, which is allowed in some other experiment, but get restricted with the. Okay, so this is only at the oscillation level.
Yes, not in systematics level.
Okay. Okay, fine.
Okay. So this is so here I show the role of alpha in the determination of Theta-2,3. So in the rate value, the rate curves are for the standard cases where there is no decay, and for green cases, what we have done is that we have generated the data using decay, but in the fit we didn't consider decay. So we fit with the standard case scenarios, and as a result of that, we are seeing that the values of the measured Theta-2,3 is not coming at the correct value, but it's shifted. And that is because there is this correlations between that alpha and the Theta-2,3, which I've shown earlier in the probability expressions. And the important thing is that for this T2HK, which is basically 2 into JD, as just Sanjeev was saying, and for T2HKK, which is JD plus KD. So basically this JD is which is very close, and also it's measuring, which is a very high statistics. It's measuring this Theta-2,3 very precisely. So these effects is very small. But for ESSNUSB, which is a second oscillation maximum, this is also wide, though the effect is much more.
So your T2HK is 2 detector or 1 detector? JD or 2 JD?
2 JD.
Oh,
the actual thing which is going to happen.
No, it will not happen anymore, Dipyaman. JD is only, they are struggling for even 1 detector. So JD is, phenomenologically one can explore, but the reality is that, T2HK is now basically 1 detector, around 200 kiloton. There is a specific number which they are aiming for. They have started the construction. So there is no possibility of 2 detector anymore in Japanese site.
Okay. But are they considering the Korean also?
Yeah, that is a separate group. They are studying and they are trying to get the funding, but there will be no contribution from Japan. The entire thing should come from Korea, and if they can get the international collaboration.
So now the second, the middle picture is much more plausible then.
Yes, definitely. Much more. No, I would say T2HK with 1 detector is sure. That we will see by 2028, maybe some portion of the detector is running and going. They have started construction, and I hope they will have the money. But 2 detector is not in their game now for JD setup, and JD plus KD may happen, but it depends on if Korean they can get the money for the second detector.
Okay, but yes, I think this JD plus KD is much more useful than this only two times JD.
Yeah, always, if you have more data at a different L by E, that is going to help in many ways, but
Right.
the problem is the funding agency is telling that you are totally relying on Japanese people for your beam. So you
Right.
are just getting the leftover. Okay, it is
Yeah,
passing
yeah.
to Japan and going to Korea.
Yes,
Though it
yes,
is free because they are getting a beam which is free.
yes.
But in neutrino, statistics matters. There are
Right.
experiments people have planned or projected on at second oscillation maxima. But the
Yes.
point is at second oscillation maxima, your stat is less.
Right.
Okay? Because you only probe a small window of the energy. And when
Exactly.
your stat is less, funding agency wants quick results. So they want event.
Right.
So you need to wait. In neutrino, the event is more important. So
Right.
I like the idea of second oscillation maxima, but in reality, that is the bottleneck for them. And that is why you see in ESSnuSB, they are thinking of 5 megawatt beam, which is really a dream. But there is no I completely agree that we should sir, we should tell them what is possible, what is not possible physics wise. So
Yes.
there is no demerit in that. There is a merit in this kind of work, but 2JD is not likely anymore. Okay.
Yeah.
Okay, this is just a comment.
Yeah, but if you see this results wise, this T2HK and T2HKK are almost similar results.
Yes.
For at least for theta 2,3.
Yes.
Okay, so the next is for the same thing I have shown for the higher octant, and all similar behavior is seen. And so this is also the octant sensitivity for the alpha equals to 0 and alpha equals to some non-zero values. For here we have done only for ESSnuSB, which is one second oscillation maximum experiments, and we see that in presence of alpha, this octant sensitivity increases when the theta 2,3 is in the higher octant. And we have also done a combined analysis, and so here this red is for T2HK, the black is for the ESSnuSB. This blue is for the T2HKK, and this magenta and the cyans are for the two combinations, the ESSnuSB plus T2HK and ESSnuSB plus T2HKK. And we see that this ESSnuSB plus T2HK gives them almost similar results as T2HKK. So basically the fast oscillation maxima helps. So basically it helps in determination of the theta 2,3, and the second oscillation maxima helps in the determination of the alpha, and they together breaks these correlations between the alpha and the theta 2,3. Also, we have here assumed non-zero values of alpha in this left figure, and 0 values of alpha in the right figure, and done these 2D plots for sine square theta 2,3 alpha planes, and we have shown this here. And again, the combinations helps in the statistics. So now I come to the second part of my talk, which is about what about the solar antineutrinos, which is based on the recent work which I have done with my Brazilian collaborators, Orlando, Pedro, and Henan. So here, this is the model for our decay, where this nu I, which is an active neutrino, which is decaying into another active neutrino, which is nu j, plus x, which is the muon. And this is the general Lagrangian, interaction Lagrangian for this type of process. And this GS is a purely scalar coupling, and this GP is the pseudo-scalar couplings. And we get this decay width, which is given by these relations, where this M is these matrix elements. And here we have two types. One is for the helicity conserving case, and one is for the helicity violating cases. And this delta, which is an important parameter, which I will show. And this is mj by mi, which m. So this is daughter divided by the parent. So it should be always less than 1 and greater than 0. So this is the differential decay width, and there is this kind of kinematic conditions between this parent energy and the daughter energies, which is given by these relations for ultra relativistic neutrinos, which is always true. So this is the simpler relations of this constraint. And for helicity conserving and helicity violating decays, this decay which can be written like this, and the lifetime is given by these relations. So mi over tau, tau I equals to ei times this gamma. Gamma is this total decay width. If we assume only one parent decays into one daughter, then this becomes very simpler, and we get this relation. So next, we divide this differential decay width with the total actual decay width and get these two relations, which is important because we will basically use these relations later. And this is the first one is for the helicity conserving case, and the second one is for helicity violating cases. And also these plus and minuses are for scalar and pseudoscalars. So for purely scalar case where this GP is 0, we get these relations, and for these plus and minus are for scalar and pseudoscalars, and this is for helicity conserving case, and this is for helicity violating cases. And purely scalar means this GP is 0, and purely pseudoscalars means this GS is 0. And finally, we have these branching ratios. If we plot these Ws, we get these relations. And so the first one, this left one, is for delta equals to 0.01, which is a hierarchical case. So basically, this the difference between the parent and the daughter is very large. And for the right one is for the quasi-degenerate case, where the difference of the masses between this parent and the daughter is not very high, and they are almost of similar masses. So firstly, for the hierarchical case, we note that there is not much difference between the scalar and the pseudoscalar cases, both for the at least for the helicity violating case. But for the helicity conserving, we can see that there are some differences between the scalar and pseudoscalar. But if we go take this delta to a much lower values, this will basically vanish, and there will be no differences. And for this right plot, there are huge differences between this pseudoscalar and helicity, pseudoscalar and scalar cases, and also for both helicity conserving and helicity violating cases. Also, we see a different behavior for these two cases. So here this blue curve goes here and the red goes there, and it is not that much. So now I come to this oscillation probability under these scenarios. So for we have to go to a little different formalism. So for this, we need these three operators, which are defined like this. So this EL is given by this, which is basically the amplitude of propagation of a state of energy EI for a distance of L without doing anything else. So it is created at 0 and goes at L, and it gets annihilated. So this is given by this relation. And in the meantime, it gets these oscillations. And then we have this disappearance, which is basically the amplitude of a neutrino state remaining, this will be undecayed. So this is a typo, remaining undecayed after propagating a distance of L along its baseline. So it goes L along this baseline, but it doesn't decay. Then this is given by these relations. So this is the disappearance operator. And there is an appearance operator. This is basically the distraction of state I with energy EI and chirality R, and creation of a daughter state in the jth eigenstate with energy EJ with chirality S, and within the distance L and L plus DL. So within a small distance, what is the probability, the amplitude that it annihilates and creates another state? That is given by this relation. But this eta is the fraction of the decay products which reaches the detector, which is basically a geometric factor which is given by these relations. Now for the solar neutrinos, as sun is very far away and it is really symmetric, so the which is very forward picked, and therefore these relations can be simplified into these simple relations, this thing. Now, the probability of transition between ith and jth mass eigenstates within intermediate states like, so it decays into one particle, then again decays into another, like this. So the number of times it happens, which is given by this term here. And where this mi tilde is written in this form, where m is this usual mass of the ith eigenstate, and this is the coming from the decay term. So for n greater than 0, the Pijn is given by this complicated relations involving lots of integrals. And for visible decay, we assume that there is only one intermediate step, and we neglect n greater than 1. And we get a simpler relations where this Pij, which is a visible decay probability given by this invisible part plus the one intermediate step part, and the one intermediate step part is given by this relation, which is now only one integral. And in terms of, again, the flavor states, when I multiply it with the P-minus matrix elements, it becomes these relations, which is much simpler than this form. So now collecting all the terms, the general expression becomes this. This is the invisible part, and this is the visible part. Now for solar neutrinos, we assume that the decay happens only during the flight between the sun and the earth. So when the neutrino is exited from the sun, then it can decay. It is not decaying inside the sun. And therefore, inside the sun, it just follows the standard MSW mechanism, and therefore we can write this as this. So this incoherent sums, and this becomes this. And so the P invisible becomes this, where this Pii is just an exponential factor. And for the visible part, we can again write in terms of these parts, which is, this is the solar part of the oscillation, and this is the earth part. And this is given by this relation. Well, here we have assumed that there is no difference between the day and night. So we are basically neglecting the earth matter effects. So this is the visible part. So including both invisible and visible part together, we get these relations for the probabilities. And finally, the flux at earth is given by these relations. So now we have this, and so we have this term. So the first part is the invisible, and the second term is the visible part. So in the important thing is that in the second term there is this integral, which is because we have a range of energies of the initial particle, and we have to integrate about that. And this integration limits is given by the kinematic conditions, which I was talking earlier. And this is from the Ej to Ej by delta square. And also in the final relations, which we are going to use, this flux contains this Wij, which I was talking about a little ago. So now, so why antineutrinos are so important? Because in the weak interactions, this left chiral neutral leptons are associated with neutrinos, and the right chiral neutral leptons are associated with antineutrinos. But if neutrinos are Majorana, neutrinos and antineutrinos are identical. So only way to say that it is neutrinos or antineutrinos is by these relations. So if it's this left chiral and neutral leptons, I mean this kind of thing. But inside the sun, only the left chiral neutrinos are produced by fusion processes. For the relativistic neutrinos, the chirality and helicity can be approximately same, up to the order m over e. So that's for this helicity flipping process, which I was talking earlier. So this process where R and S are not same. So the first, these left chiral particles changes these helicities during their flight and transform into right chiral particles, which then appear in the terrestrial detectors as antineutrinos. So therefore, the appearance of antineutrinos from the sun can be a clear signal of decay, because we don't expect antineutrinos other than some new physics. For this channel, which is this nu 3 to nu j bar, so the flux is given by these relations. The first term, the invisible term, is 0. And for the antineutrino part, and for visible part, for the antineutrinos, only visible part is there, and therefore this thing. So the point is here that earlier for solar neutrinos, so we didn't consider this nu3 to nu-j, but now as S13, the sign theta13 is known to be non-zero, this becomes a non-zero term. And now we can explore this nu3 decay also in solar case. So earlier also the sun was able to only constrain the nu1 and nu2. Now we can constrain nu3, as I am going to show in the next few slides. And therefore, if neutrinos are Majorana, then solar antineutrino spectra can be used to study the decay of nu3 and put bounds on the nu3 lifetime. So what is the antineutrino flux expected in this case, where this nu3 is decaying into nu1 bar? And here I have shown only for the pseudoscalar case. Also for scalar case, similar plot can be generated. So the solid lines are for the standard solar neutrino fluxes for various channels, which is unoscillated. And for the solar antineutrinos, so in case of decay, this decays, this nu3 to nu1 bar, with this lifetime tau3 over m3 of this value and delta of this case, that is the hierarchical case, we get a non-zero flux for the solar antineutrino, and this is what we should expect. The important thing here is that there is this spectral distortion of this flux due to the decay, and also the another signal is that these beryllium lines, which get wider, which was earlier the monoenergetic lines, now becomes the continuous spectrums because of the decay in for antineutrinos. Now, what we did is we take this Camland data for antineutrinos, which is basically the bound of antineutrinos from the Camland experiment, and we have matched this plot using their model, which was just a probability of transformation of neutrino to antineutrino, and then we did our analysis. And for Borexino, we took this table and matched with this table our analysis, and using this again, this neutrino to antineutrino conversion probability of these values. In both cases, we have used only the so this flux. So using our analysis, we get the following results for the lifetime of nu3. But okay, so I have cut and paste from our paper, so there is no axis, but this is the same axis. It was basically one above another. But anyway, these are tau3 over m3. And this is a delta. In this plane, we have shown the results. So these shaded regions are disallowed, and this part is the allowed region. For
one, I didn't understand your previous slide.
Okay.
Go to Borexino slide. So for Camland, what you have matched, like you are discussing this possibility in the context of solar neutrinos, right? So yeah. Okay, for in the context of Borexino. So for Camland, you take the oscillation parameter or what? We matched our simulation with the ABHA publication, means what?
With this plot. Okay. So this I should, if I get this event, then I should get this result.
No, so you are suggesting that these are the Camland data points or what?
Yes, these are Camland data points.
Camland reactor antineutrino or what?
No. This is the solar. Yeah, they have these IBD detectors, but they are measuring the solar from the sun. What is the antineutrino flux from the sun?
Okay, so this is Camland with solar neutrino.
Right.
And what?
Yeah, this is the red one.
Camland with solar neutrino. And what is the interaction process? Like in Camland, it is an IBD detector.
Yes, so this is an IBD process. So it's inverse beta decay process.
No, but inverse beta decay, then it has to be the nu-e bar, not nu-e.
Yeah, I have read it in this nu-e bar. So we are doing the antineutrinos.
Okay, so you are saying that if this physics is there, this possibility, yes, then from sun you have some solar and electron antineutrino nu bar,
Right.
and they will add to some IBD event
Right.
on top of the IBD event that you see from your reactor.
Yeah, so this is the backgrounds. All the backgrounds, these are given here. So
Okay.
they have used some cuts and whatever and get this background.
So how did you get this 5.3? It is just by a fitting, or what kind of fitting you have done?
Well, this is given in their paper that they have this anti-neutrino, the upper bound of this.
This is the bound they have given.
Yes. So I have matched with this bound using this model. So just a neutrino to anti-neutrino conversion probability, no,
So
without any
they
distortion.
are saying that this, what is this quantity 5.3 into 10⁻⁵? What is this quantity? This helicity flip?
No. This yes, the probability of neutrino to anti-neutrino conversion without any oscillations.
So this is 10⁵ in Kamlan, the bound that they have given.
Yes.
Now come to Borexino. So in Borexino, they have given you the number of events, right? In the energy given. This is the table from Borexino. But this is scattering event, right? Nu electron scattering, no?
No, this is also nu bar, IBD.
This is nu bar. You are
IBD.
sure?
I think so, but I will check it in.
Okay.
I think yes.
So they have also a paper discussing this neutrino antineutrino conversion. This is what you are saying.
Yes.
Okay, and then they must have talked about IBD in their detector.
Yes. So this is a 2019 paper. I have taken this from this paper.
Okay, so these are the bounds that you are showing are given by these two respective papers on this helicity flip.
Yes.
Okay, then got it. Then
so this is the result we are getting for these channels. So this is for nu3 to nu1 bar, and this is for nu3 to nu2 bar. So these both are allowed.
In what context? In which experiment?
It's a combined. I'll show the individual later.
This is solar plus Kamlan. What?
This is no. This is Kamlan plus Borexino. These two.
Okay, this Kamlan plus Borexino. Okay.
Yes.
So did you simulate their antineutrino event? Like, what kind of event they expect if this helicity flip is happening with the detector properties and the cross section, everything?
We didn't consider any systematics. We just wanted to show that this is possible for this type of. We can put bounds on the nu3 from the solar neutrinos. That's the main target of this paper. So we didn't consider many details of this kind of things.
So how did you get this plot? What kind of simulation you have done to get this?
Okay, plot? So we take the flux, this flux, and take the cross sections, which is this IBD cross section, and integrated these to get the thing.
Okay, but no resolution, nothing basically.
No, so it will be a little less. But actually, I checked with resolution. It was taking very large time to do this integration, and there was some effect, but not very much.
It's just flux time cross section.
Yes, but with resolutions, I did one check, but
no, there are some other issues also. But I understand the philosophy. So it is flux time cross section times some probability with helicity flip.
Right. Yes. No. The probability is inside this flux. So this.
Flux. Yeah, it is changing. It is giving you the altered flux of antineutrino.
Right. So it's a flux times cross section. Because I didn't take the systematics and all these things because it was taking too much time, because this integral. So you have this extra integral I have to do every time.
Right. Okay.
So this is the result, and this is for nu3 to nu1 bar, and this is for nu3 to nu2 bar. And this is the blue one is for the pseudoscalar cases, and for the red one is for the scalar cases. And we can see that this for pseudoscalar the limit is much stronger, and also these limits are around this 10 to the power 3, 10 to the power 4 in this range, which is much stronger than the long baseline because of this large distance from Earth to Sun. And also we see that these limits are stronger for the nu3 to nu1 bar case than the nu3 to nu2 bar case. And this is because of the sine square θ12, which is coming into the probability part. So for one, that is cos square, and another is for sine square θ12. So that is giving these differences. And also the case is that for this is so weak that we don't get any limit for the scalar case here. Next, this is for the different. I have shown here the different for the different experiments what is happening. So this red one is for Borexino and the green one is for Cameron, and the blue one is for SUM. And we can see that it is mostly dominated by the Cameron result. Borexino is not playing much role here. And here this is for the normal hierarchy case. So where this nu3 is decaying to nu2 bar, nu3 is decaying to nu2 bar, all that I showed in the earlier plot. And also we have taken this the usual case, which is the nu2 to nu1 bar case. And this is much more strong because there is this no sine square theta 1,3 suppression here. Also for completion, we have shown these results, which is for inverted hierarchy case. So now we can have also inverted hierarchy case because this nu2 can decay to nu1 just like before, and also this nu2 can go to nu3 bar, and nu1 can also go to nu3 bar. And again, these limits is almost of the same order as the previous this one, but for this the last case, this is very weak limit because due to the MSW effect, there is not much nu1 to start with. So that's the reason we have these weak limits here. So now I come to my conclusion. So neutrino decay is one of the possible new physics effect that can be explored in the future experiments. So as L is large for these experiments, T2HKK and ESSnuSB, so they can give very good sensitivity to the decay. But of course, less than the solar, but it's okay. So addition of a first oscillation and second oscillation maxima, it can complement each other because the first oscillation maxima experiment can measure the theta 2,3, and the second oscillation maxima can measure the decay very well. So they can break these correlations. So they can complement each other. For the solar neutrinos, the observation of antineutrinos from the sun might be a signal for decay. Also, so this observation of theta 1,3 not equals to 0 by Dave allows us to put very strong bound on the lifetime of nu3 from the bounds on the antineutrinos from sun. So these are some of the future interests. So also, as I have now doing this along this lines and solar experiments, also I'm interested in atmospheric experiments like IceCube, INO, or Hyper-K, and also the supernova neutrinos. Also, I'm interested in doing this type of studies where we just check what are the signals of the new physics at the near detectors of the various future long baseline experiments, which is now growing a industrial like thing. And the third one is now I'm very much interested in this machine learning techniques, and I'm learning machine learning. So I want to see if we can explore these machine learning techniques in the neutrino phenomenology to make it more efficient. Also, I am interested in working on open quantum system aspects of the neutrinos like decoherence and so on. So thank you for listening to my talk.
Thank you, Dipyaman, for a nice and comprehensive talk and telling us how you have probed decay in various experiments. So now we can have some question, though we had some question during the talk, but now if somebody wants to ask any question or have some discussion, please feel free to ask Dipyaman any queries, comments, or questions. It is very important for students to speak up. You know, I'm sure they don't understand many things, but if you don't understand, that is the purpose of a seminar, that you raise your voice, you ask, and try to learn. So if you have any question, you can ask. Otherwise, I need to assume that you have learned everything and you know whatever Dipyaman has presented, and then maybe I will ask you the questions.
Okay, hello. Am I audible?
Yeah.
Okay, so I just wanted to know, in your second work, you have not considered that day-night asymmetry.
No.
Okay, so will it change anything? Means if you consider the earth matter effect also?
It might change, but I think the day-night asymmetry hasn't been observed. So that's why we didn't consider this. And also we just wanted to show here that this can be possible. We can put the constraint on the lifetime of the nu3 from the solar experiment. So earlier we used long baselines to do this, but now we can do it with solar experiments also. That's the main motto of this paper.
No, that I want to correct you basically, Dipyaman, that solar day-night asymmetry has been observed. So you read the paper, the observation of solar neutrinos in super Kamiokande, and read the latest paper or any latest talk you go through. They have seen around 2.8, or if you read any global fit paper by Mariam Tortola, it is clearly mentioned. And this day-night asymmetry has been playing an important role to remove the tension between delta M21 square measured by Solar and Kamla. So day-night asymmetry has been observed by Super Kamiokande in using solar neutrino data, and it is around, I think, 2.7 sigma or around 3 sigma. I forgot exactly the number, but it has been observed.
But 2.7, is it that much significant?
But yes, that much information is very important.
That's true. It's a hint, I can say. But
it's not a hint. It has been like, they are just lack of statistics, but it is there. Day-night asymmetry is there. And it's a very important phenomena. And it is helping to reduce the tension between delta M21 square measured by Solar and Kamla. It's just a matter of fact that Super K is doing better and better day by day. It's a old horse, but still giving you money. So they are reducing the threshold, improving background rejection, new simulation technique. So you just read the solar neutrino analysis of Super K, and they are doing very good job. So solar day-night asymmetry has been observed. In your case, that it will have some impact or not, I don't think it will go. It is going to change much the scenario. But one thing, if you don't assume helicity flip and just assume that because θ13 non-zero brings you nu3 in the solar analysis, it's a 3-flavor analysis, right?
Yes.
Otherwise, nu1 and nu2 are sufficient to explain solar.
Right.
So now, why can't you just assume that nu3 decays to something? So then you would expect some less flux maybe in solar neutrino experiment, not nu3 going to nu1 bar, but nu3 goes to nu-x plus Majorana.
So nu-x is your invisible boundary, you were saying.
Invisible.
But I think there is this already the neutrino oscillations, which is a large effect. It will be a background, right thing. So it will be a very small effect. So that's why we don't see this is suppressed by the sin square θ13 term, right? So
I'm just asking that this invisible decay, like if nu3, is it possible that nu3 is decaying to some invisible component? Because in the solar neutrino case, you start with nu-e, and then on the way, it disappeared to nu-mu, or with now θ13 also nu-tau, and you see the survival of nu-e, right?
Right.
Now, in that picture, if you just think that your nu3 is decaying to some invisible component, will that be hidden into the uncertainty of the oscillation parameter or systematics, or what?
I think so. That's what I think.
No,
because this sin square θ13 is very small, right? So this will be always dependent on the sin square θ13 term, which is so small.
Because nu-tau is very small. Nu-tau is very small, basically.
Right.
It is θ13 suppressed.
Right.
Like whatever it goes to, nu-mu, now it is getting divided further, basically, right? So I understand that, but I'm just thinking that the scenario that you explode with long baseline, that there you didn't consider helicity flip.
No.
Right? So if you consider the same situation in solar, I think your bound will be very less. I think, right? Or
like you are saying this neutral current measurement. So this neutral current measurement should be a little less. in this case. But it will depend on sin square theta 1 3. The difference.
Right. Neutral current measurement. Good. If you measure all the flavor, like a SNO experiment, okay, where you measure all the 3 flavor, right, which solve the solar neutrino puzzle, right? So there, if something is decaying to invisible, then you will see less neutral current event, right?
Yes.
So maybe there are already papers on that.
Maybe, but I think this effect will be very small. That's what I guess. Sin square theta 1 3.
Here you are comparing against 0 because you don't have any antineutrino.
Right.
So if you have one event, that is a discovery at certain confidence level. Okay, and there you have a huge background basically.
Exactly. That's what I'm saying.
Okay.
But actually now we are also doing another work with Andre and Monique Broto and also other. So here we are considering both neutrinos and antineutrinos kind of things.
Neutrinos and antineutrinos means?
So this helicity conserving and helicity flipping both. Not antineutrinos, we are not considering antineutrinos, only neutrinos.
I see.
But this is under work now.
Very nice. So any question for Dipyaman? So it seems like, people are hesitating to ask you question. Maybe they can ask you confidentially over email or, and some other forum. But I would again encourage that, young students, postdocs, they should ask questions because the whole purpose of this meeting is discussion. So anyway, Dipyaman, very nice talk and thank you for joining us and telling us what you have been doing. And good. So if you can share your slides with us, we will post it on our social media handle. So
hi, Dipyaman. Can you hear me?
Yes. How are you?
Yeah, I'm fine. So
you are in Italy or what? No.
IFP.
Oh no. I thought you got a postdoc in.
Yeah, means suppose, yeah, means I have some doubt. When you are considering this this visible decay, okay, so then means what is the means you are considering these things in matter or in means outside of the sun? Means
no, this is during the flight of after the exit from the sun. So inside the sun,
you have not considered anything.
Case.
You have not considered anything inside the sun.
No.
So means the point is means because I am asking because when you consider this visible decay, okay, then the analysis will be difficult when we consider the matter effect. Okay.
Yes.
Did you consider that thing anywhere? Means in your art-based, accelerator-based experiments?
In accelerator-based experiments, yes, we have considered matter and we have solved numerically.
No,
but
that
for this
is invisible decay. But
no, I have not worked on visible decay in the long baseline experiments.
There is a paper, Shomiron, where Orlando with Pilar Coloma studied a visible decay in some crude way in case of long baseline. And I think they have also taken matter effect, but it's numerical. Okay, but in sun, I think I read the paper, Dipyaman has mentioned that within the sun, he is not touching anything. So he is out of the sun and then, just vacuum probability is changing with all these hypotheses.
actually, the problem is that when
I cannot hear you. Can you speak aloud? Your mic is having some problem or something.
You are telling
not
me?
you, Somiron.
Yeah, problem is it's automatically gone down.
Now I can hear.
Yeah, the problem because I was asking this when they are considering U, this U, but if there's a matter effect, then U changes. Okay, so how they calculate that U in the presence of this non-Hermitian matrix? Okay, they have not told in the paper. They mainly the Pilar Coloma and this Orlando Perez paper.
Okay, actually, we are also working on that also. Okay, so if we can talk later about this. So I am actually reading that paper also, so I can tell you later. But I think that they numerically do this.
Yeah, means if it's they have done it numerically, then they should tell somewhere. But yeah, that paper is not clear to me, means at least that's why I'm asking. Means you are working with Orlando Perez, so probably he know those things. That's why I'm asking.
So yeah, okay.
Okay, means you just inform me. Means get some time.
Okay, sure.
Okay.
So if there are no more questions, let us thank Dipyaman for his seminar, and good luck, Dipyaman, with whatever you are doing, and stay safe and
Thank you.
recover quickly, and thank you for joining us.
Thank you.
Okay. Bye.
Bye.
Bye.